All right, at the beginning of any real analysis course, we're going to start out with sets and functions. We always start out with sets. This video is going to be basically just all sets, set theory, and then we're just going to briefly introduce functions and how functions are related to sets. You might wonder why, set theory seems very abstract, and it is, and that's kind of why I wanted to add in functions at the end here, because I think the main reason sets and set theory is introduced in real analysis, not the entire reason, but the main reason is because they want to introduce you to how they work with functions. So that set theory was formalized, not formalized, by some guy named George Cantor. You might hear of Cantor's sets and Cantor's theorems. And I actually looked this up this time. I didn't just, say I don't know the year. He apparently formalized it in the 1870s. So our guy Cantor, props to him. Let's give him a little shout out. Then we can dive right into set theory. So set theory obviously is all about sets, how they work, their properties, and how they relate to other mathematical objects. So what is a set itself? A set is, I guess, a very informal definition, possibly formal definition, is a set is an unordered collection of distinct objects. Each object is called an element. So, two key words here, unordered and distinct. The word collection is kind of vague. For now, we can just, usually sets are written in this notation, this bracket notation. You might have this set of just 4 numbers, 0, 1, 2, 3. Since sets are unordered and they're distinct, this is actually equal to the set 3, 1, 0, 2. They're the same sets because they have the same elements. It doesn't really matter about the order of the set for a set. Other objects, other collections in mathematics, the order does matter, but for sets in particular, order doesn't matter. And like we said earlier, sets they're distinct. So we're not really going to have 2 3s in this set. It wouldn't really make sense in this case. So if we have if an element is in a set, if we say X is in some set S, we write that as X, and then this symbol here, S. So this is just shorthand of saying X is in the element. X is an element of the set S. But we don't really always just have these arbitrary finite sets here. So there's something called set builder notation. So let's say we want to talk about all even numbers. How about all positive even numbers? How about that? Or all positive integers. Let's erase. Gotta learn how to erase in this thingy. So we're gonna use set builder notation to define the set of all positive even numbers, natural numbers in particular. So we're going to say this. We're just going to call it S. S is equal to 2n such that n is an element of the natural numbers. All right, so this notation may look a little weird if it's the first time you saw it. So all we're saying is we're defining this set S. S is just what I called it here. We can actually call it something else. We can call it, you can just call it evens, basically, if you want. You can just call this evens. That's the name of the set. And it's just, so what you do is you put the bracket in, and you actually have this definition here on the left of the colon, of how we define all the elements in the set. And we have a description of the variable. So we have 2n such that n is a natural number. So what is that set going to look like? So that's going to be, we'll just say evens. Again, this is just the name of the set, it's not important. So we're gonna kind of just enumerate it out. It's gonna be 2, 4, 6, 8, blah, blah, blah. Pretty obvious, I know, it's just even numbers. But the point is, this is how you can use the so-called set builder notation to actually define a particular set. Similarly, the odds can be defined as 2n plus 1. N is a natural number, or we can say n is a positive. We can say n is a natural number, or 0. So the odds are just going to be 1, 3, 5, 7, blah, blah, blah. They're just the standard odd numbers. So we have the set builder notation, and there's other things we can do. We can do squares. We can do, so square is equal to n squared, such that n is a natural number. Or we can even make it simpler. We can just say the integers is the set itself. We can just say integers equal to x, such that x is an integer. That's just simply saying basically all integers. That's a set of all integers. And these are all infinite sets that I've mentioned here. We'll go more into infinite and finite sets. So a set that contains no elements is called the empty set, or it's called the null set. And this will be very important later on, the null empty set. And we have something called, we also have this concept of subsets of sets. So a subset set is kind of exactly what you would think it is. So if we have the set 1, 2, that's actually a subset of the set 1, 2, 3, 4. Because this whole set 1, 2 is contained within the set 1, 2, 3, 4. Another example is the set 3, 5 is a subset of the set 1, 3, 5, 7. So that's how we would define a subset. There's a more formal way to do that, and we'll probably formalize it later. But a subset is essentially just one set is a subset of another set if every element in that original in the subset is contained in the set. So every element in here is contained in here. Just a couple more things we want to look at. So we have this concept of unions and intersections. The intersection of a set A and B, let's say we have two sets A and B, are all the elements such that X such that X is in A and X is in B. The union of a set is the set of elements X such that X is in A or X is in B. So just a couple of quick examples of the union and intersections. Let's take the unions first. So let's take two sets A is equal to 1, 2. And the union and B is equal to 2, 3. The union of these sets, A union B, are all the elements that are either in A or B. So that's going to be 1, 2, and 3. But the intersection are the elements that are in both A and B. So in this case, it's just going to be 2, because 2 is the only element that's actually in B and also in A. So that's why it's the only element in the intersection. But in the union, we're basically just taking all elements that are in either of those sets. And even though 2 is in both sets, again, since the elements are distinct, we only write 2 once. So there are other properties of sets we can go into. We won't go into too much more detail until we need to. This is the basic stuff. You really need to just know how a set's defined, know that a set is unordered, they're distinct, they're elements. Know this notation, this set builder notation. My next video will probably be just examples of this, just to get the concepts down. And so these are how sets work. And yeah, the question is, well, why do we discuss sets in real analysis? Sets are probably more important in other classes. You know, sets are very abstract, but they're important in real analysis. They're important in calculus and stuff like that because of what we would call functions. We all learn functions in high school math, middle school math, and it's a pretty basic definition in high school and middle school, but it's more rigorous when you get to real analysis. So we can define a function in the following way. Let's say we're given sets A and B. A function is a mapping or association or rule that associates every element in A with some element in B. So the key here is that we have 2 sets. We have the set A. Let's say these are all the elements of the set here. We have like 6 elements. And this set B. For a function to be a function, every element in A needs to be associated with some element B. It's possible that they are associated with the same element, but every element in A needs to be associated with an element in B. So that's why we need set theory to talk about functions. Functions are rigorously defined using the concept of sets. Functions actually associate one set to another set. If you take the set of integers, you could think of a function that maps them to the even numbers by just saying the function is 2 times. So if we call this set x, the function could just be f of x equals 2x. And then the set over here is the even numbers. That's very informal, and we'll go into more rigorously defined examples of functions, but that's how it works. That's how a function works. A function is a rule that associates an element with one set to another. So that's set theory and that's functions. Next video, we'll go into a couple examples just to drill the concepts down. And then after that, we can start talking about all the cool real analysis stuff, all the fun stuff.